Welcome to the Explainer. Look, if you're project engineer, an AV integrator, a consultant, or an ops director, you already know the struggle. The evolution of visual displays has basically always been this brutal tug-of-war. On one side, you have brute force hardware, literally cramming more and more LED chips into tighter and tighter spaces. And on the other side, you have smart algorithmic processing. Today, we're going to unpack exactly why that balance is fundamentally shifting and why the entire AV industry is rapidly moving away from purely physical density toward algorithmic efficiency with virtual pixel COB architecture.
All right, let's dive into this. Here's our roadmap for the briefing. First, we'll tackle the physical density problem. Then, we'll break down how virtual pixels actually work, crunch the comparative engineering data, outline some strict integration criteria for your projects, and wrap up with the algorithmic future of the market. Let's get to it.
Part 1. The physical density problem, or as we like to call it, the sub-millimeter challenge.
To really grasp the solution, we have to understand the core paradigm shift. Think of a traditional rigid tile mosaic. That's real Pixel COB. It relies on a direct, one-to-one physical mapping. Every single logical pixel in your image demands a dedicated physical cluster of red, green, and blue diodes. Now, compare that to virtual pixel. This is essentially a brilliant optical illusion. It completely decouples the spatial and temporal processing, totally tricking the human eye into seeing a continuous, ultra-high-resolution surface without actually needing that massive density of physical hardware.
Now, you might be wondering, why do we even need this illusion? Well, because you simply cannot solder millions of extra diodes per square meter without facing some massive penalties. When you push below a 0.9 millimeter pitch with real pixels, your diode count increases exponentially. And you know what that means. Manufacturing costs absolutely skyrocket. Worse yet, especially for the operations directors tuning in, you get a severe elevation in thermal loading, your delta T goes way up, and you see a massive spike in baseline power requirements. It's just an unsustainable way to build a screen.
Section 2. How virtual pixels work. This is where we transition away from just throwing more hardware at the problem and start leveraging human biology.
The technical term for this magic is subpixel multiplexing. Simply put, it's a time multiplexing and spatial algorithm. Instead of that rigid one-to-one layout we talked about, the system dynamically shares physical LED emitters. Think about an RGBG layout, where you add an extra green LED. By doing that, the hardware can share light emitters across multiple logical pixels on the fly, based entirely on the luminance and chrominance required in that exact millisecond. Because of this, one single physical pixel cluster can actually generate up to 4 virtual pixels.
But here's the thing. The software is really only half of the equation. The other half comes down to this specific number, 1 arc minute. That is the foveal resolution limit of the human eye. The fascinating optical principle at play here is that below this 1 arc minute threshold, our visual system biologically cannot differentiate individual subpixels. It automatically and flawlessly blends them into unified color information. Basically, our brains are surprisingly easy to hack, and virtual pixel technology exploits this exact biological limitation perfectly.
So how exactly does the screen pull off this illusion? It happens in 3 rapid-fire steps. First up is spatial virtualization, which generates virtual points in the empty gaps just by blending the brightness of adjacent physical pixels. Next is temporal virtualization. The display rapidly switches these states, often using 60 frames per second subframes, relying entirely on the persistence of human vision to superimpose the images. And finally, algorithmic correction kicks in. Advanced control algorithms apply dynamic contrast and average luminance corrections to sharpen everything up and instantly fix any edge blurring.
There is a catch, though, and it is absolutely crucial for system integration. Minimum viewing distance, or MVD, is the critical factor here. For this optical trick to work flawlessly, the MVD must be greater than or equal to 1.2 meters. At 1.2 meters or further, the human visual response to a virtual pixel screen is literally identical to a real pixel screen. You eliminate perceived visual artifacts, you get maximum sharpness, and you do it all without the redundant hardware.
Okay, Section 3, Engineering Comparative Analysis. Let's move away from the theory and look at the hard empirical data.
Let's methodically compare the specs side by side for a target 0.9 millimeter resolution. To get a perceived pitch of 0.93 millimeters, real Pixel COB requires a physical pitch of 0.93. But Virtual Pixel achieves that exact same perceived resolution using a much wider, less dense physical pitch of 1.25 to 1.56 millimeters. And because it uses way fewer diodes, look at the ripple effect. power consumption drops to roughly 60 to 65% of the baseline. The operating temperature drops by 5 to 8 degrees Celsius. And the contrast ratio, it actually increases from 10,000 to 1 up to over 12,000 to 1.
Just look at this drastic drop in power consumption. By relying on algorithmic generation instead of physically illuminating millions of redundant diodes, Virtual Pixel COB caps out at a maximum of about 65% of the power draw of a traditional system.
That translates to direct energy savings of 35 to 40%. If you are a facility manager running a 24/7 control room, this drastically reduces the life cycle cost of the installation over its lifespan. It's a massive financial win.
And the secondary physical benefits literally cascade from there. Less physical diode density inherently means you have a larger black resin ratio right on the board itself. That physical black space is exactly what pushes those contrast ratios over 12,000 to 1, giving you incredibly deep blacks. Plus, that lower diode count drops your surface operating temperature by 5 to 8 degrees, which takes a huge thermal load off your facility's HVAC systems.
Moving on to Section 4, Integration and Selection Criteria. Knowing the specs is great, but knowing exactly where to deploy them is what makes or breaks a project.
We have to clearly separate our deployment environments here. For control rooms, corporate setups, and 24/7 operations, where that viewing distance is 1.2 meters or more, Virtual Pixel is practically mandated for its power and thermal efficiency. However, for broadcast and MCR studios, where you've got cameras pulling tight shots at less than 0.8 meters, you still absolutely need real Pixel COB. You have to have that physical density to avoid more ray effects interfering with the camera lenses.
Now, if you are an AV consultant, how do you actually verify what the manufacturer supplied you? It's pretty simple. You can run the single pixel software test. Send a command for one white pixel on a totally black background. If it's virtual, you'll actually see multiple physical pixels light up dimly to share that load. You can also run high-resolution text testing, since virtual pixels naturally anti-alias and smooth out the jagged edges on really fine fonts. Or, if you want to be completely sure, just do a microscopic physical inspection of the RGB chip clusters while the screen displays pure white.
To give you an idea of how seriously the industry is taking this shift, just look at this internal directive from Unilemon's technical management. It aggressively states that any control room project with a viewing distance of 1.2 meters or greater simply cannot bypass Virtual Pixel COB architecture without submitting formal engineering calculations. They want to see exactly how you justify the massive power, HVAC, and lifecycle costs of choosing a real Pixel alternative. Virtual Pixel is rapidly becoming the undisputed default standard.
Finally, Section 5, the algorithmic future. Let's look at how this breakthrough is actively reshaping the economics of the global display market. The massive manufacturing giants are heavily driving this adoption. Take BMTC, for instance. They recently hit an insane 20,000 square meters of monthly COB capacity. They now dominate over 50% of the entire industry COB shipment volume, and their aggressive push into virtual pixel algorithms is a huge driver behind that scale. So the crucial takeaway is this. The maturation of virtual pixel algorithms is completely collapsing hardware costs. At the exact same perceived pixel pitch, actual LED chip costs decrease by roughly 2/3, and the cost of driver ICs gets cut in half. This is the exact technology allowing us to build stunning 4K resolutions on massive 136-inch all-in-one screens without charging premium, unattainable hardware prices. Software has permanently decoupled ultra-high-definition visual quality from exorbitant hardware costs.
Which leaves us with this final, provocative question for your next engineering project. When you spec a display, are you paying for physical hardware or are you paying for visual perception? If human biology literally cannot tell the difference past 1.2 meters, why on earth would you pay the hardware, power, and thermal penalties? Definitely something to think about before you sign off on your next installation. Thanks for joining us for this explainer, and we'll catch you on the next one.